All right. Last class, we were learning about gases. We learned about the ideal gas law. Does anyone remember the ideal gas law? PV equals nRT, and we used it for a couple of different things. Oop, haven't done that one yet. We used it for a couple of different things. One of those things was making simple gas laws. The nice thing about the ideal gas law is that we just have one of each variable. We don't have to have two states of pressure, two states of volume, two states of temperature, two states of number of moles like we do with our simple gas laws. Instead, we have this value R, which has a whole lot of units, and our units need to match these units. So the values that we use for P, V, N, and T have to match what we're using with our ideal gas constant. Typically, we are going to be using the ideal gas constant that we see here or something that looks like it. You can find ones with more decimal places if you need or want them. Other stuff that we can do with gases beyond using the ideal gas law and our 4 simple gas laws that we learned. In our kinetic molecular theory, which we started the chapter off with, we learned that the components of the gas mixture act independently of each other. We're treating all of the particles the same, even if their identities are different. In reality, that's not exactly how it works. There are some more complicated factors than that, but we don't cover it in this class. The pressure due to any individual component in a gas mixture is called the partial pressure, the pressure of one gas. The pressure of one component in a gas mixture. We call it the partial pressure because there are other things that are in the gas mixture. You add all the partials up, you get the full, the total. So partial because it's not the entire pressure. The partial pressure of any component is that component's fractional composition. Fractional composition is percent composition divided by 100. So percent divided by 100 equals the fractional composition, which usually has, I think, the symbol chi. It's X, but it's got a little tail in the front. The partial pressure, let's say that our component, our gas, is A. Is equal to the fractional composition. How much of the gas is A as a decimal times total pressure, P sub TOT. We've got some examples coming up. We're also using this in lab this week. For those of us that were in the Tuesday lab, I talked about it very briefly and I wrote some stuff up on the board. For the rest of us, we're learning it here. So the air in our atmosphere is a mixture of gases. It's about 78% nitrogen, 21% oxygen, a little bit of argon, a smaller amount of carbon dioxide, and some other things even smaller amounts than that. The nitrogen molecules N2 exert a certain pressure, 78% of the total pressure. That is roughly independent of the presence of the other gases. So the other gases being there doesn't change the amount of pressure that they produce, at least not to any great extent. And the oxygen molecules also exert a certain pressure, which is about 21% of the total pressure, matching their percent composition of the air. So let's say that we've got a total pressure of 1.05 atmospheres. Maybe we've got a little bit of weather, so the pressure is higher. Pressure often changes when weather systems are moving around. That's why we've got like old people that are like, "Oh, my knee's creaking, it's gonna rain soon." They can feel the change in pressure in their knee for some reason, and so they know that there's like a low pressure front So a storm's coming, or however weather works. Let's say that we've got a total pressure of 1.05 atmospheres. What would be the pressure of nitrogen? Nitrogen is 78% of the total pressure. So 78%, divide it by 100 to turn it into a decimal, and we get 0.78. This 0.78 is our chi N2, our fractional composition of N2. So then to find the partial pressure of nitrogen, it's not a question mark, it's 0.78, the fractional composition of the nitrogen, times the total pressure, so the nitrogen is exerting a pressure of about 0.82 atmospheres. So N2 by itself is 0.82 atmospheres of pressure because of the volume, because of the temperature, the number of moles of gas. That's how much pressure it's exerting. And we've also got a joke for us. The optimist says the glass is half full. The pessimist says the glass is half empty. The chemist says the glass contains 50% H2O as a liquid, 39% N2 as a gas, 10.5% O2 as a gas, and some other things in there too. The glass is full. It's just half gas. All right, more partial pressure stuff. A gas mixture contains 64% methane, 36% ethane. Those are the little siblings of propane. If the total pressure is 1.44 atmospheres, what are the partial pressures of each component? So we're looking for two partial pressures, one for methane, one for ethane. What are some things that we're given? We're given total pressure. Total pressure is P sub T OT. 1.44 atm. What other things are we given? We're given some percentages. Methane is 64%. Ethane is 36%. We can turn those into fractional composition. Fractional composition of Me and Et. Those are how they're often abbreviated, if they're substituent groups at least. Those values are going to be their percent divided by 100%. If you can do that math in your head, you're more than welcome to just do that math in your head, because all we're doing is moving the decimal place 2 spots to the left. So 64% becomes 0.64, 36% becomes 0.36. And now that we have their fractional compositions and we've got the total pressure, the pressure of, I don't know why I keep doing a Q, the pressure of some component is the total pressure times the fractional composition of that. We've got the fractional compositions, we've got the total pressure, so we can plug them into this equation and we'll get out the partial pressures. So partial pressure of methane, partial pressure of ethane. The total pressure is 1.44 atmospheres. That's for both of them. And their fractional compositions are 0.64, 0.36 respectively. So we get 0.92 atmospheres and 0.52 atmospheres. Do we have any questions about how we did that? You will probably get this P sub A equals PTOT times chi A on an exam on your information sheet. You'll have to know what the symbols mean. So you must know what the symbols mean. Does anyone notice anything about our partial pressures and how they relate to our total pressure?
When they're both added, they equal the total pressure.
If you add them up, 0.52 and 0.92 atmospheres, it adds up to the total pressure. We have a name for that phenomenon. It's Dalton's law of partial pressures. So Dalton's law of partial pressures say that the sum of the partial pressures equals the total pressure for however many components you have. So the total pressure is equal to the pressure of component A plus the pressure of component B plus the pressure of component C plus however many terms you want to add onto there. Because of rounding, this is also an equation that you'd be given on an exam, by the way. Because of rounding, it's sometimes off by a little. You should be within like 5% or 1%, depending on the numbers you have and how many significant figures and all that. It's the same as percentages. Percentages sometimes don't always add up to 100% just because of the way that things round out. But it'll usually be like 99% or 101%. Same thing can happen with partial pressures. It should end up to be correct on the exam at least. So that's Dalton's law of partial pressures, our third thing relating to partial pressures. All right, let's say in some crazy universe, we have a sample of hydrogen gas and that's mixed with water vapor. Who could imagine it? For the people in the Tuesday lab, that's literally what we did. Or for the people in the Thursday lab, that's what we do in the lab. So that's why I'm saying that it's crazy, because who could imagine it? The mixture has a total pressure of 734 torr. The water vapor has a partial pressure of 22.5 torr. What's the pressure of the hydrogen gas? I'll rewrite Dalton's law. And then give you a little bit of time to calculate the partial pressure of our hydrogen. All right. So we've got our hydrogen gas. It's mixed with water vapor. How many components do we have in our gas mixture? Cool. Lots of people advocating for peace in the classroom. Showing me 2. That's correct. So our specific form of Dalton's law of partial pressures, we're going to have our pressure total is equal to the pressure of the hydrogen gas, H2, plus the pressure of the water vapor, H2O. What's our total pressure? It is 734. So total pressure 734 torr. And our water vapor has a partial pressure of 22.5 torr. So pH2O is 22.5 torr. We want to know what is P sub H2, what's the pressure of our hydrogen gas, the partial pressure. We have P total, which is one of our variables in our Dalton's law. We also have pH2O, another of our variables, and pH2 is the last thing, so we can solve for it. If we subtract the H2O from both sides, that will move it from the right side to the left side. So we'll do that and flip it left and right, and pH2 is equal to P total minus P sub H2O. We've got both of those things, so we can solve. So 734 torr minus 22.5 torr it's 711.5 torr. We get to round for the ones place. So 712 torr would be our final answer. This problem didn't specify what units we needed. On the exam, you'll be told what units you need to provide, or the answers will have units with them. But since it didn't specify here, 712 torr is correct.
Okay, I thought
Yeah.
when doing minus or subtraction or addition, we round to the decimal.
The 734 doesn't have anything past the decimal place. So that would be the least number of decimal places.
Oh, gotcha.
It's easier to see if we stack them. So we'd cut off there. So the second one is our last digit. The 5 lets us round up. Questions? We're cruising. Our lungs perform best at an oxygen partial pressure of around 0.21 atmospheres, which is around 21% at 1 atmosphere. Basically just means that our lungs work really well when we're at about sea level. If you go higher into the mountains, at higher elevations, the total pressure decreases, the percent doesn't change, the pressure drops, and so the partial pressure of oxygen also drops. It's still about 21%, but the total pressure is lower, and this gets more and more severe the further up you go. So if you're up at like a mile or 2 of elevation, if you're up hiking in our Sierra Nevada mountains, you might notice that you're getting winded a little bit more easily because there's less oxygen in the air. It's still 21%, but the pressure total is lower, and so there's less oxygen available for you to breathe in, so it makes you run out of oxygen a little bit more. If you get too high up, then you run into hypoxia, which is oxygen starvation, and that can occur to a severe extent at partial pressures of less than 0.1 atmospheres. People that summit Everest typically bring oxygen unless their bodies are already adapted for low oxygen, like these summiters here. Other really tall mountains, I think they also bring oxygen for. Like I think if you're climbing K2, you also bring oxygen. Oxygen toxicity also occurs. So it was hypoxia on the previous slide, it's toxicity here. I don't usually test you on these because this isn't a medical class. Oxygen toxicity can also occur if you get too much of a good thing, it's a bad thing. Too much O2 is bad, actually. But it has to be a lot. It has to be more than about 1.4 atmospheres. So if you're at elevated pressure of oxygen, then you might start twitching, get tunnel vision, and have convulsions. This could occur if you're breathing pressurized air and your mixture isn't correct. I've never been scuba diving, so I don't know if that's something that happens frequently. I'm guessing it probably doesn't. Pressurized air also has an increased partial pressure of nitrogen, since nitrogen is the main component of our air. Air is mostly N2, and so you can also get nitrogen narcosis. Narcosis is like sleepiness, I think. Also called rapture of the deep. This is apparently similar to being tipsy, which doesn't sound too bad, honestly, but probably not a good thing if you're like 50 meters underwater. Deep sea divers, people that are below 50 meters, use a specialized mixture of gases like heliox. Heliox is helium and oxygen, and this avoids nitrogen narcosis, since helium doesn't really react with your body, and you can adjust the amount of oxygen that's in your gas mixture so that you don't get oxygen toxicity. The reason that we mentioned heliox there is because we'll be using it in a later example. So what we're doing in lab this week is we're collecting a gas over water. So if you take a beaker or some other container and fill it up with water and set it upside down, the water will stay up in this container because there's pressure pushing on it. For this water to leave, it would have to push against the pressure of the air, and then there would be nothing at the top here which would make a vacuum. Vacuums don't like existing. So unless you're plugging something into here, putting some gas in, it's just going to stay being full of water. If you pipe some gas in, though, then that relieves the pressure that would form from that vacuum, and the water level can drop, and you collect your gas up at the top. You've maybe done this if you've taken a bath and you were a child. I think I did this as a child when we took baths sometimes. You trap a little gas. Where'd that gas come from? So you can collect your gas, and then it's not connected with the rest of the air that's around us. So you're not getting the nitrogen, the oxygen, the other stuff that's in there. But because there's water in there, some of that water is turning into water vapor. And so we have to adjust for the pressure of the water vapor. To do that, we use a table. So let's say that hydrogen gas was collected over water at a total pressure of this many millimeters of mercury and a temperature of 25 degrees Celsius. What's the partial pressure of the hydrogen gas? So we had a total pressure and a temperature. We want to know the partial pressure of the H2. The first sentence tells us that the hydrogen gas was collected over water. That means that the only two things that are in there are hydrogen gas and water vapor. So our total pressure is going to be the combination of our pressure of H2 and the pressure of H2O. This time, though, we were given a temperature instead of a pressure of our water. As it turns out, water has pretty consistent behavior. And so if we know the temperature of the water, we can figure out what the vapor pressure of the water is probably going to be, or will be. So we're looking for 25 degrees Celsius in our table. 25 degrees Celsius, and then the matching vapor pressure of the water is this 23.76 millimeters of mercury. So pH2O, 23.76 mmHg. We were told that the partial pressure is 758 mmHg. Our pH2 is the total pressure minus the pressure of the other component, water. So 758 minus 23.76. And it's 734 mmHg. Apparently I took out the heliox example and forgot that I took it out. Oop. Oh well. All right, other stuff that we can do with gases, because I know that you are all thinking to yourself, really, Mr. K, that's all? You don't have more stuff to test this on? Yep, sorry, I do. We just hadn't gotten to it yet. So some other stuff that we can do with ideal gas law is stoichiometry. Who remembers what stoichiometry is?
It's kind of like the ratios, like for example, like with the BLT that you said, like for every 2 slices of bread, you make 1 BLT.
Yeah, it's the ratio of your different reactants and your products. Just how many reactants go in, how many products come out. You can compare 2 of your reactants. You can compare a reactant to a product. If you've got multiple products, you can compare your products too. So stoichiometry, we're just thinking of ratio of 2 things, specifically in a chemical reaction. So when we have reactions that involve gaseous reactants or gaseous products, the amount of gas is more often specified in terms of volume with given temperature and pressure rather than the grams of the gas, because it's a little bit annoying to try to measure the mass of a gas. So instead, we just take the temperature, we get the pressure of the room, and we can figure out volume of whatever container it is, often pretty easily. We can use the ideal gas law to convert pressure, volume, and temperature to moles. So starting with PV equals nRT, if we want number of moles by itself, that's N, you just divide both sides by retweet, switches from the right side to the left side, and N, number of moles, is equal to PV over RT. And then we can use the ratio, we can use the stoichiometry to convert from this moles of our gas, to other quantities. Or we could get the number of moles and figure out the pressure, the volume, or the temperature. There's lots of different fun mix-ups and change-ups that we can do at this point. Let's look at an example. Sulfuric acid is the industrial chemical produced in the greatest quantity, almost 45 million tons, 2,000 pounds per year in the United States alone. It's prepared by this overall chemical reaction. So you put in some sulfur, some oxygen, some H2O, you get out sulfuric acid as an aqueous solution. And you can use sulfuric acid for lots of things like acidifying your blueberry fields and clearing your drip lines in a field, making sure that they don't have hard water buildup. Do we think that this chemical reaction is balanced? Yeah, it's probably balanced. I'm just going to say it is balanced. And the way that we could guess without actually checking if it's balanced, we've got coefficients. Usually people aren't mean and just give us like some of the coefficients, but not all of them. Usually if they're giving us coefficients, that means that it's balanced. And now the question of the text. The first part was all flavor. What volume of O2, specifically in liters, at temperature, pressure, is required to produce 1 ton of H2SO4, sulfuric acid? What are we finding? We are finding volume of oxygen. So this is another one of those word problems that feels like it's backwards, perhaps. But we've got our question word what all the way up at the front, and volume of O2 is right after that. So we're finding volume of O2. What's some information that we are given that we might choose to start our problem with? We are given pressure. And we're also given temperature. Can we find liters of O2 with pressure and temperature? Or is there something else that we need to? Let's write out our ideal gas law. We're finding liters of O2, that's volume. So we're going to divide both sides by pressure to move it to the right side. Volume is equal to nRT over P. We'd go and look up R on our periodic table / information sheet. So we're looking for volume. We have pressure. Check. We have temperature. Check. We've got R because it's a constant. Check. Do we have N? We do not have N, not for O2. So we need nitrogen for O2. Not nitrogen. Number of moles for O2. If we get to moles of O2, that's the last variable that we need for our ideal gas law. So we could go from moles of O2 to liters of O2 with the ideal gas law. Do we have something that we can use to get moles of O2? We can't use the ideal gas law because we don't have volume. Do we have like a grams of O2? Do we have another chemical that we could use to get there? We could use molar mass. Do we have grams of O2? Because we could turn grams into moles. We don't have grams of O2, do we?
We have kilograms.
We've got kilograms of what? O2? Not O2, different chemical. H2SO4? So we've got some stuff that's related to H2SO4. Do we know how our O2 and our H2SO4 are related? Both have oxygen. Do we have a ratio between the two?
For every 3 oxygen, 2.
Yeah, for every 3 O2, we can get 2 H2SO4. This ratio, 3 moles of O2 equals 2 moles H2SO4. That's our stoichiometry step. So if we have moles of H2SO4, we can use our 3O2 equals 2 H2SO4 ratio to get the moles of O2. And we can get to moles of H2SO4 because we've got kilograms, we've got a mass of H2SO4. So if we convert that kilograms into grams, we can use molar mass to get to moles. So starting with kg H2SO4, we can work our way through our solution map to get all the way to liters at the end. Do questions about any of the steps that I'm doing here, that I'm proposing here? The only thing that we're doing here that's really new is that we're connecting all of these ideas together. We've done kilograms to grams. That was like chapter 2, chapter 3. It was early chapters, right? So it's maybe been a while. We might want to revisit our prefixes. We use kilo and milli a lot. We've done grams to moles. That's just molar mass stuff. That was also a while ago. I think it was chapter 5 maybe that we learned about stoichiometry ratios. We can convert from moles of one chemical to moles of another chemical using the numbers that are in our balanced chemical equation. And then the most recent stuff that we've learned is using ideal gas law to convert moles to liters or other variables. So let's get started because we've got a couple steps. So 907.18 kilograms. What does kilo equal? What does it stand for? It is 1,000. So 1 kilogram equals 1,000 grams. So if we multiply by 1,000, that will get us out of kilograms and into grams. And then we need a molar mass for H2SO4. I'm going to give you 2 minutes to get the molar mass of H2SO4. All right, our molar mass for our H2SO4, hydrogen, sulfur, oxygen, we've got 2 hydrogens, 1 sulfur, 4 oxygens. We get to do some multiplication. The reason that I was giving us some time to work on this is that we will need to use these skills again. If not on the next exam, certainly on the final. So if you're like, hey, I can do like 4 of the 5 steps pretty confidently, but I can't do that 5th step, whatever that 5th step is, Logan can help you. Logan would love to help you. Go to his SI session, eat some candy. All right, so we get a molar mass of 98-ish grams per mole. And so we need to divide. We've got grams on top here. Grams is on top for our molar mass. We're going to divide by our molar mass. And we'll add in the chemical labels for both of these as well, since I know some people like that. We didn't start with chemical label. Okay, so our H2SO4, our grams cancel out. And now we're in moles of sulfuric acid, moles H2SO4. We've got a ratio of 3 to 2 that we can use here. We've got 2 moles of H2SO4. We have H2SO4, moles of H2SO4, so we want to use our 2 moles on the bottom. And our O2, we've got 3 moles of O2. Moles of H2SO4 cancel. We would now be in units of moles of O2. And let's go ahead and get a number here so that we've got something, and then we can do our ideal gas law as a separate thing. Strictly speaking, you don't have to do that, but it might be nice. So 907.18 times 1,000 divided by 98.072 times 1.5. 3/2. We've got many moles. 13875 and some change moles. O2, that's a lot of moles. And now we can plug this into V equals nRT over P. V equals, I'm going to leave it as N because we already have the number written out right next to it, but we'll write the rest of the things. We also have to ask ourselves, why are we here? No, sorry, wrong question. Do our units match up with our R value? They do not. So we have to convert millimeters of mercury and degrees Celsius to match our R value. So mmHg can turn into atmospheres. Divide by 760. (22 plus 273.15). (295.15 Kelvin). Now our units match. So we've got N, R, we need T, 295.15 Kelvin, and then on the bottom, our pressure, 0.980, and all the other stuff that comes after it, atmospheres. Atmospheres cancel, kelvins cancel, the moles cancels. With the moles, we plug all this into our calculator. V equals giant number of moles times 0.0821 times 295.15 divided by 0.98 and change, and we get syntax error. We love to see it. All right, no syntax error this time. 34291.1847 liters. And we're going to round it off for 3 significant figures. Questions? Mr. K, why would you make such a fun problem for us, maybe? How could you synthesize so many ideas together to test us? Your exam problems generally will not be this involved. If anything, there will be one of these, and that's because I pressed the violence button. All right, other stuff related to gases. There is such a thing as a molar volume at standard temperature and pressure. Standard temperature and pressure, STP, is 0 and 1. 0 degrees Celsius, 1 atmosphere. What's special about 0 degrees Celsius? That's when water freezes into ice. This is freezing cold. Do we like being freezing cold? No, probably not. We don't like being freezing cold. We're going to bundle up if it's freezing cold. What's special about 1 atmosphere? Where is it 1 atmosphere of pressure?
Sea level.
Sea level. Do we like being at the sea? Probably lots of us like being at the sea. We're on the beach. So there's a little bit of bad. We're freezing cold, but at least we're at the beach. And it can be cool, pretty, to be at the beach when it's cold. So if just remembering 0 degrees Celsius and 1 atmosphere of pressure doesn't help you, maybe you can imagine what it's like to be in Pismo in the dead of winter. Christmas at Pismo. Some hot clam chowder maybe to warm up. Sounds nice. We love a little bit of Pismo chowder for Christmas. All right, the molar volume, the volume of 1 mole of gas at STP, we can calculate that. We are finding volume with inputs of 1 mole, and we're also at STP. Our ideal gas law, PV equals nRT. This isn't something you have to be able to do. You can do it to come up with this number. V equals nRT over P. And we know what our numbers are for those. Our number of moles is 1 mole. R is always the same thing. The temperature is 273 Kelvin, and the pressure is 1 atmosphere. So what's really cool about this is that after we cancel out all of our units, we've got a 1 on top and a 1 on bottom, and those don't do anything. And so we're just doing R times our temperature. And we get a value of 22.4 liters. And again, this is the liter per 1 mole. So the molar volume of an ideal gas, a gas that behaves ideally, is 22.4 liters per mole at STP. So when we're at STP, if we've got 1 mole of gas, we know that it's going to take up 22.4 liters of space. If we've got 22.4 liters of a gas at STP, we know that that means we've got 1 mole. So this is a convenient conversion factor. I'd recommend memorizing it in conjunction with our STP. I'm going to say it's nice to have memorized. I do usually put a question about what are the conditions for standard temperature and pressure. All right, let's say that we are looking for liters of nitrogen at STP to form 9.85 grams of NH3. We're looking for liters of nitrogen. We are told that it's at STP, and this should activate us like a sleeper agent. Our brain should be screaming at us, 0 degrees Celsius, 1 atmosphere, clam chowder in Pismo. And we should also be thinking 22.4 liters equals 1 mole. That's what STP should trigger in us. And we're given 9.85 grams of NH3. Our solution map, grams, NH3, we can turn that into moles, NH3. We can turn that into moles, N2, we can turn that into liters of N2. That's what our full solution map will look like. We're going to need a couple things. We're going to need some molar mass, just one. It takes longer to write it out than it does to put it in the calculator for me. But we'll write it out so that we can see it, because it's maybe been a minute. Cool, we did it. We got it. 17.031 grams per mole. We need a ratio to connect our moles of one chemical to our moles of another chemical. We get our ratio from our balanced chemical equation. 1 mole N2 equals 2 moles NH3. And then we need something for this last step, something that connects moles and liters. Do we have something that connects moles and liters? What's that up there? Yeah, we've got the molar volume at STP. .4 liters equals 1 mole. And then our calculation will look like this. Let's do it different. 1 mole NH3 over 17.031 grams NH3. Grams NH3 cancel. We can do 1 mole N2 over 2 moles ammonia NH3. Moles NH3 cancel. We have moles. We want to go to liters. 22.4 liters equals 1 mole. To get rid of the moles, we're going to put the moles on the bottom. 1 mole on the bottom, which means the 22.4 goes on top. So moles cancel. N2 and liters are still there. So we get liters N2. So we do 9.85 divided by 17.031, also divided by 2 times 22.4. Or you multiply everything on top, write it out, multiply everything on bottom, write it out below that, then do your division, you get 6.48 liters of N2. Any gaseous questions? Then we're done with gases.